We're going to look at conversions and coterminal angles in this lesson. So we want to use periods to determine equivalent values. We want to find what a coterminal angle is in either degrees or radians and find exact value sine and cosine if you have one of these coterminal angles. All right, so a function is considered periodic with a period p if your function at x is equal to some other function where you evaluate the same function at x plus whatever the period is, where p is a real number. So anything where you get an equivalent value in sometime later, that's a periodic function. A graph of one of these periodic functions repeats itself indefinitely. If f is known over one period, then you should be able to find it everywhere else since the graph repeats itself. What does a graph of one of these periodic functions look like? Here's some examples. You can see this graph here is the recording of someone's voice humming. You can see that there is some period, this graph is periodic here. It repeats itself every so often here. So one period of this looks like this here, where we get back. It looks like that's the spot now where you get back to that same equivalent point right there. So it repeats itself over some time. Here's another example of a periodic graph. So remember, whenever you get back to that same value sometime later, that's a period. So here, this stopping right here would not be one period because it should repeat itself right afterwards, meaning I should do the same thing that was happening right here, which is going up. So one full period would be right there. Now I'm in that same spot I was before where this graph does the same thing over and over. Same with this one period of this would look like this. Now I'm back to that same starting spot I was before. So periodic functions repeat every over some amount of time and get you back to that same starting value. Another example is time. Time's an example of a periodic functions. Things like seconds, minutes, hours, days, months all have a period where there's equivalent times on the clock or calendar. So we'll do some examples with something you're familiar with before we jump into using it with trig here. So let's say the minute hand is on the 0 mark. Where is the minute hand 152 minutes from now? Well, what we want to do here is figure out what's the period. If we're talking minutes, the period on the clock for minutes, it repeats every 60 minutes. So the period here is 60. So there's a couple ways you could do this. One is to remove the number of periods, so you could subtract to get there. So one way we could get this would be to take 152 minus 60. If we did that, that would bring us to 92. We still would not be within one period of it, so we repeat the process. 92 minus 60, that would bring us to 32. So now we know after going through 2 full periods of this, we'd have 32 left over. So we know the minute hand would be on the 32-minute mark. So that's where it would be located. Now we got that by subtracting the period, so you can do that. But what if this had been a really big number? What if it had instead been a number like 9,621 minutes? That wouldn't be an efficient way to keep subtracting 60, the period, from that multiple times. We could get there, it'd take us a long time. So is there another way we can do this? Yeah, another way you can do it is to divide by the period. So if you take 152 and divide by the period of 60 minutes, let's see what we get here. So if we divide that, so you want a calculator for this, 152 divided by our period of 60, gives us this 2.53333 repeating. Um, what does that 2 represent in this? 2 here would be representative of the number of full revolutions around, or rotations. We're not interested in how many times it's gone around. We're interested in that extra stuff. That's like the extra stuff that was over here. So what you want to do next now is subtract the number of full revolutions. So we're going to take the 2.53 repeating here minus 2 to get the number of full revolutions, okay, which would be 0.53. Now if we want to get that back into the minutes, we want to multiply back by the period. So if we take this 0.53, the extra stuff that is not a full revolution, and multiply that back by 60, that should tell us the number of minutes. And if we do it right, it should come out to be 32, the same thing we got before. So let's jump back on calculator. If we do minus the 2 revolutions and then times back by our period, we should get 32. So that's a more efficient way of doing these ones where it's not dependent on how many revolutions there might be. All right, let's look at B. Where was the minute hand 85 minutes ago? Now this is different. Now we're moving backwards. This would be similar to on our unit circle moving clockwise. So what we want to do on this one is think of this 85 as negative here. So if we had negative 85 minutes. Let's do our same procedure as before. So let's divide this by the period 60 and see what we get. So if we do that, negative 85 divided by 60, that's going to give us negative 1.416 repeating. Okay, we want to know what's that extra amount there. So on this one, we want to get that so it's positive. So it's going to go negative 1 time around. So that if we add, let's add 1 to that on this one. So we're going to take this, add 1. So that would give us just this without the 1 on there. So it'd be negative 0.416 repeating. Let's multiply that back by our period. And see what it gives us. So if we times this back by our period of 60, it tells us it was 25 minutes ago. Now that it's 25 minutes before the 0 mark on the clock. So what that is telling us is if you go back 25 minutes, that would be it. Now that still doesn't answer what hand it was on. So what you'd want to do here is add that period on 1 more time and see what you get. So if you add 60 on here 1 more time, that would tell us it's at the 35-minute mark. So 35 would be the hand that this is on. And you could do that here again, add 60. It would be at the 35-minute mark. So that if you're going backwards, you got to think of that as negative. All right, why don't you pause, try these 2 out. These are talking about months. And so you got to think about what's the period for months here. What would the period be? And then this one is days of the week. So if your period is days, what would be your period here or there? All right, so pause and try these out. All right, let's see what you got. So on this one, yeah, one key thing is to notice it does say ago here, so you want to make sure it's negative. So take that number, divide by 12, which is the period if you're in months, and you get negative 250.16 repeating. That negative 250 means that's how many revolutions. So add that on and you get this times it back by our period of 12. And you can see all that on the calculator here. You get -10, which means it was 10 months before January. You could count back months, 10 months from January if you want, or if we add on the period here, you get 2. So that would be 2 months from January. So if you move 2 months from January, February, March, looks like it would be March here. So if you got March, nice job. All right, the other one, here our period with days would be 7, and this is in the future here, so it'd be positive. So if you take 184, divide by 7, you're going to get this. That's 26 weeks in the future here, so let's subtract off that 26. Now we just got the extra times back by the period of 7, and we get 2, so it'd be 2 days from Wednesday, which would be Thursday, Friday. So you got Friday for this one. Nice job. All right. The point here, P, which is any point's going to have an XY value on the unit circle, is called the terminal point. So your terminal point is where it ends. So the measure of an angle is determined by the amount and direction of the rotation to the terminal side. So if your angle is positive, remember we're moving counterclockwise to there. So there's the terminal point. If your angle's negative, you're moving in the clockwise direction, that number of degrees or radians, and that would be your terminal point. So terminal point's where you end. Coterminal angles then are angles in standard position in which their sides coincide. So coterminal angles, we use rotations and periods to find coterminal angles. We are going to focus on finding the coterminal angle that is less than 1 rotation. So what we're looking for is what is that same angle that is less than 1 rotation, which in radians would be 2 pi, and degrees would be 360. So we want that equivalent angle that would be between 360 and 180. So depending on how you get angles here, you could get angles that are in fact already less than 360 or 2 pi. So these would be angles 30 and 3 pi. If we're looking at an angle of 390 though, we can see that that one is more than 360. So we would want to find what's an angle that's the same as this or coterminal. This one would be easy to find if we just minus 360. We could see that 30 degrees, that what we had over here is the same. These other angles here would also be coterminal to 30 degrees. If you divide and find that, all these angles here would in fact end up being the same as 30 degrees. Here's another one that we can quickly check. This negative one, if we would add our period of 360 to that, would also get 30 degrees, same as what we had over here. So that would also be coterminal to 30 degrees. All right, so they want us to find what's the coterminal angle to 29 pi over 6. We could do this in radians, but I think most of you are more comfortable with degrees, so we'll convert this to degrees first. Remember our conversion factor 180 is the same as pi. So first we're going to convert this 29 pi over 6. We're going to times by 180 over pi to get the angle here in degrees. We'll use a calculator to do this quickly here. So if we do this on 29 times 180, and we're dividing it by 6, so this is equivalent to 870 degrees. Okay, so now we're going to use that same procedure we were doing with some of those time problems to figure out what's the coterminal angle to this. So first thing we want to do is divide this now by our period, which is, in this case, degrees, so 360. So we're going to take 870 divided by 360 degrees to see how many revolutions we're doing. So on our calculator, let's divide by 360. So it's 2 revolutions and a little bit more. So we get 2.416 repeating. All right, so let's subtract off those 2 full revolutions. So we're going to minus 2 here. So that leaves us with 0.416 repeating. And then we're going to multiply that back by 360 per period and see what the coterminal angle is. So I'll do those same steps on my calculator, minus 2 times back by 360, and this should give us the coterminal angle. So the coterminal angle here would be 150 degrees. Now, one thing with this problem, usually if they start the problem in this case radians, we probably should end up find our answer also in radians. So let's multiply back by our conversion factor to figure out what this is. So let's multiply by pi over 180. And if we do that, we're going to get 150 pi over 180. We can simplify that. For sure the zeros here would cancel if we divide it by 100. And 3 goes into both of those numbers. And so the coterminal angle here looks like 3 goes into 5 times, or 15 5 times, 3 goes into 18 6 times. So it'd be 5 pi over 6. That's the coterminal angle. That's the coterminal angle to what we had up here. All right, your turn. Why don't you pause the video and try this one out? All right, let's see how you did here. So first thing I did, convert this to our degrees by multiplying by your conversion factor here. So you should have got 7,650 degrees. Divide by our period. Looks like it's going to be 21 revolutions here with a little bit more. So subtract off the 21 revolutions. That gives you, looks like 1/4 of a revolution. Multiply back by 360, our period here, to get that. So here's the calculator work of doing that. So if I times this back, you can see you get 90. So now 90 degrees, let's use our conversion factor to get that back into radians since we started in radians. And if you do that, you should get this is coterminal with pi over 2, because 90 would go into 182 times. All right, if you're asked to find the exact value of some of these angles that are greater than 360, we can use that same process and find the equivalent coterminal angle. So example on this one, let's figure out what's the, they want us to find cosine of this. What's the coterminal angle to 19 pi over 3? So if we get this into degrees here, multiply by that, now we got 19 times 180 divided by 3. Looks like that gives us 1,140 degrees. Let's divide that by our period here, so divided by 360. So if we do that, looks like we're traveling around the circle 3 times with a little bit more. So we get 3.16 repeating. Let's minus off those 3 revolutions. And if we do that, we get that remaining amount, and then we're going to multiply that back by 360 and that'll give us the coterminal angle here. So it looks like it's the same as 60 degrees. All right, so what we'd want to do now is this is equivalent here to cosine of 60 degrees. We should be able to figure that out from our unit circle now. So if you had our unit circle and we had a 60-degree angle, what is that ordered pair going to be? Well, remember, this is 1, it's a unit circle. This would be half the amount, that's our x value. And then if we times it by square root of 3, that would be square root of 3 over 2, so that would be our y value. If we're finding cosine, remember cosine, that's our x value. Another way you can remember cosine is adjacent over hypotenuse, so that's that 1 over 1, we would get 1/2. So this value should end up being 1/2 would be the answer. Same with this one, should give us 1/2. Okay, you can check these with the calculator. If you're doing this one though, make sure you're not in degrees. We'd want to be in radians here, so make sure radians is highlighted. So if I get out of here and type this one in, cosine of 19 pi over 3. Hit enter. As you can see, we do in fact get 1/2 there. So that's a way you can find coterminal angles and then figure it out. Now, also, you should be able to also do these ones if you know some of those approximation values that we had. So we looked at in previous lessons some of those common numbers that you get when doing these ones. So if you get this approximation of 0.866 with all those other numbers, remember that's an approximation of square root 3 over 2. You get that approximation of 0.070 stuff, that was that approximation of square root 2 over 2. And then the other ones that would come up would be like 0 and 1 would also come up there. You know, if 0.5 comes up, that's 1/2. So let's see if we can get some of these other ones here by doing that. So here, going back, what's this one? So let's try typing it in here. We did sine of 413. And you got to be in radians again. Pi over 4. That gives us this. That was our approximation, 0.707, a square root 2 over 2, and it's negative. So this answer would come out to be negative square root 2 over 2. Which means this must be coterminal to some, it's a sign value, it's negative. So it must be coterminal to either something in the 3rd quadrant or 4th quadrant there. Let's have you pause the video, see if you can do these two, find the coterminal angle for number 1 there, and see if you can find the exact value for 2. All right, let's see how you did. So this first one, change it first to degrees. You should have got that many degrees. Divide by 360, it's 2 and a little bit more, minus the 2, multiply back by the period. It's the same as 300 degrees. If you multiply back by your conversion factor and simplify, you should have got 5 pi over 3 as the coterminal angle. For the second one, well, let's do that same thing with the angle to figure out our coterminal angle here. So you got convert, this is the same as negative 945 degrees. Divide by our period, and it's negative 2.625. Multiply, or sorry, let's add on 2, so that's negative this. Times by 360, you get negative 225. I'm going to add 360 one more time. That's the same as 135 degrees. So if you go around here, that's past 90 with another 45. So we're looking at that 45, 45, 90 degree triangle. We know when the hypotenuse is 1 because it's on unit circle, this is going to come out to be square root of 2 over 2 and square root of 2 over 2. With it being in the 2nd quadrant though, that means the x value would be negative, the y value would be positive. Cosine's the x value, and so this should come out to equal negative square root of 2 over 2. Just checking it with the calculator, I just put in the original problem there of cosine negative 21 pi over 4, you get that approximation. It is negative like we got, and remember 0.707 is an approximation for square root of 2 over 2.